By writing the README first, we can explore different approaches to the user experience of our CLI. We could think through the entire CLI right now, but we'll leave the other subcommands for later, and instead focus on the fact that we know that we will have multiple subcommands in this course, and design the command on which all of the other ones rely: write. By focusing on the README, we'll focus on the experience of the users who want to use our tool. In this case, the first thing they'll hit is the title Digital Garden, which is the name of our tool, and a description, a CLI tool for the creation and maintenance of digital gardens. Now, I've already written this course, so I know that we're going to have multiple subcommands. But when we think about how somebody is going to write in their digital garden, we can think about the things that they're going to want to do. They'll want to write something. They'll want to search their documents for specific tags. They'll maybe want to publish a site from those documents. So we can immediately see there are multiple separate actions we are going to want to take on a digital garden. The most basic action we'll want to take is to just write something. In this case, our CLI name is going to be garden because it's fairly easy to type. It's 6 letters, and it's a lot shorter than typing out digital-garden. The subcommand we're going to use to write is called write. So we've already defined the name of the binary that we're going to use by writing the README. Thinking about what else we might want to do with this write command, we might already know what we're going to write about. I might want to write about, say, iterators in Rust, in which case I'll want to give the command a title when I say that I'm going to write. In other cases, I may be taking notes, or I may not know what I'm going to write yet, or what I should title it. So we'll make sure that the write subcommand can accept a -t or -- title flag with the title that we'll use to create the file name with the content that the user ends up writing. I'll add a description here and fix the heading level so that write is under commands. Write will open a new file to write in our digital garden. Since we don't necessarily know what we want to title what we're writing, we'll leave the title as optional and ask the user for it later if they don't provide it up front. This README describes our first subcommand. We'll have a binary named garden with a subcommand called write that takes an optional argument called title. After sketching out some of our README, we'll want to initiate a new cargo project. We'll use cargo init for this. Cargo init defaults to creating a new binary application. This creates a binary crate inside of our package. You can choose between initializing a binary crate and a library crate when using cargo init. If we look at the file list, we can see a gitignore, a source folder with a main.rs in it, and a cargo.toml. If you're familiar with other ecosystems, such as NPM, cargo.toml will look familiar to you. Instead of a package.json, this file is written in TOML, but it contains the same information, such as the name of our package, the version, the authors, the edition of Rust that we're using, and then we can specify our dependencies, including our dev dependencies. The gitignore contains a single entry, /target. /target is where all of our code is going to compile into whenever we do a cargo build or a cargo run. The code that will compile into our binary is located in source main.rs. In this case, we have a small program with a single main function that uses a printline macro to print hello world. If we run cargo run, cargo will call out to rustc to compile our application and run it. In this case, cargo run selects the default binary. It compiles our package, digital garden, v0.1.0, and my package is located in users Chris egghead digital garden. It'll tell us when it's done and how long it took, and it'll tell us which version it's running. So we compiled a debug release. So inside of target, inside of the debug folder, we'll find a binary called digital garden, and that prints hello world. After running cargo run, we can see the path as target debug digital garden. That means the name of our binary is digital garden, which is the same name as the package. If we bring open cargo.toml, we can confirm that. We can change the name of the binary by using a bin field. Note that because cargo packages can have multiple binaries, this is an array. We'll rename the binary to garden and specify the path as being source main.rs. We could change the path, but it is conventional to have the default binary be source main. while the default library is source lib. And now we can see that we run target debug garden when we run cargo run. If we look in target debug, we can see a binary called digital garden and a binary called garden. This is because digital garden is left over from the first build when the binary was still named digital garden, while garden is the new binary name. Our main function uses the printline macro, which prints out hello world when we run it. We're going to replace the printline macro with a to-do macro. And now when we run our application, we'll see that the thread panics, and it panics with a specific message, not yet implemented. To-do has a very specific benefit over printline, in that it will allow us to type check our program without actually completing the implementation. How it does that is out of scope for this lesson, but we do have two other options that we could have used instead as well. The to-do macro itself indicates unfinished code, as specified in the documentation. This can be exceptionally useful if you're prototyping or just trying to type check the code without actually implementing the implementation. Unimplemented and panic are two macros that do the same thing as to-do. All three of these macros will panic and crash the application. The reason we aren't using panic here is because panic should be used when a program reaches an unrecoverable state. What we have here is not an unrecoverable state so much as an intent to implement future functionality. For similar reasons, we aren't using unimplemented, because unimplemented just says, well, we haven't implemented that code, whereas using to do indicates some intent to implement that in the future. Unimplemented carries no such connotations. That said, if you feel like panic or unimplemented is better for your use case, feel free to use them. The to-do macro is quite useful and exposes what happens if future functionality in our program panics. But this could be more readable and also contain more information, while also including colors. To achieve this, we'll use color_err. Color_err includes an error report handler that we can attach to our main function to handle things like panics and errors in a more visual way. Since we will have actual human users using our CLI, this will make for a better user experience. If you're used to other package managers with add, remove, and upgrade functionality, like npm or yarn, you'll want to use cargo edit. By using cargo install cargo edit, we gain access to the add, remove, and upgrade subcommands. I already have it installed, but you'll see slightly different output when you install. Now that we have cargo edit installed, we'll do cargo add color_err. And note that I mistyped the package name with an underscore instead of a dash. This is a fairly common mistake for me to make, and I'm happy that cargo edit handles this for me. If we look at the dependencies in our cargo.toml, we'll see color_err specified as 0.5.10. While we don't have to use color_err result to be able to use it in our type signatures, we'll do it here to make our type signature a little bit shorter and make it easier to use the result type in future functions. If you're less familiar with how use works, note that it's not actually an import, and that writing the full path in the type signature will achieve the same result. We modified our main function to return a result with a value of unit. We aren't allowed to return anything other than unit inside of the result here. For more information about how result works and why it works, you can read in main and tests in the Rust edition guide. Note that, like we said before, we don't actually have to use different exports. We can use the fully qualified path instead. In this case, we'll use the color_err install function. On docs.rs, we can search for install, click the install function, and see what the return type is. In this case, install takes no arguments and returns a result of unit and report. This is the same type that we have in the return type of our main function, so we can use a question mark to propagate the error back up to our main function if this function fails, and otherwise, we can just continue with our program. Now when we cargo run, we'll see color_err getting downloaded. And after our program is built and run, we'll see that there's new output. We can see the source location, including the file and the line number. We can see the message that was created from our to-do macro. And we can see the application panicked, crashed output. As we move forward in building out our CLI, different errors will add additional context to these error messages. This will make it such that if a file doesn't exist, for example, we know which file we're looking for and why, as opposed to just saying, file doesn't exist, fail. We haven't shown off everything that colorize can do here. In addition to panic handling, colorize allows us to track additional information in the context of our errors and include suggestions for what to do by taking advantage of the distributed tracing infrastructure that the Tokyo project has produced. We'll see more of how this helps as we build out the CLI. The structopt crate allows us to derive argument parsing functionality from our struct definitions. The name is a play on structopt and allows us to derive the structopt trait, as well as specify various attributes, which will indicate how to handle various fields in our struct. We'll add structopt to our project using cargo edit, like we did with colorize. Note that in our cargo toml, structopt showed up at version 0.3.21. Back in our main.rs, we can use structopt. And then we can write our structs. In this case, we have an option struct with a subcommand field called command. This means this command enum will be what defines our different subcommands. We use an enum here and not a struct, because while structs can have multiple fields at the same time, an enum can only have one option at one time. So if we had another variant in our enum, say search, we could only use write or search. We couldn't use both at any given time as a user of the CLI. Our subcommand enum has a single write variant right now, with an argument called title that is an optional string. By default, all fields are positional arguments when it comes to deriving structopt. That means if we left it as is right now, the command would work like garden write my title. This isn't what we wrote in the readme in the beginning, so we'll choose to change it. In the structopt attribute macro on the field level, we can use short and long to both account for -t and -- title in our CLI. Note that because we're deriving this, structopt will inspect the type of title and know that this is an optional flag. After we install colorize, we can let opt equals opt from args. From args is a function placed on the opt struct by deriving structopt on it. We'll also debug using the debug macro to display any of the arguments that get passed in. This will let us visually debug as we get started and get used to using structopt. We can cargo run, and cargo will download and build structopt into our binary. Note that when I run cargo run with no arguments, we get help output. That help output also includes subcommands. Help, which prints this message, and write, which we haven't documented yet. If we want to call the write subcommand for our binary, we can do cargo run write. The application crashes as expected because we still have to do, but we also get the debug output. The debug macro gives us a file name, a line number, the name of the argument, and the value it equals. In this case, we have an opt struct with a command field that contains a write variant with a title of none because we didn't pass one in. This debug macro is also why we needed to derive debug when we derived structopt. If we didn't derive debug, we would get that the opt struct could not be formatted using the debug formatter. There's a couple lines of help telling us that the debug trait is not implemented for opt, and a suggestion to even derive debug or manually implement it. And it also tells us why that's required. If we put the debug trait back in the derive call, and we call our binary directly, we can see what it'll look like when a user uses it for the first time. When we pass -t, because we've specified the short flag on the title field in our write variant, we can see that the title field is sum a title. Sum is an option type, which is what we specified here. if we run our binary with the help flag, we can see some documentation for the help command, as well as the fact that our subcommand doesn't have any documentation. Also notice that the name of our binary in the help output is the package name, not the binary name. Let's start by fixing that. We can use the structopt attribute macro with the name argument set to garden to change this. Now when we run help, we'll see garden as the output. If we want to write a little bit more about the CLI, we can use triple slashes and see that whatever we write is output below the binary name and above the usage. We can also write documentation on the subcommand level. Here we can see that the documentation takes the first line of our comment and uses it as the short description under the subcommands. If we instead pass help to a subcommand, we can see that the full description is shown, and that the binary name now has the right subcommand attached. We can keep doing the same and document our flags as well. And now we see that the T flag, or the title flag, for the right subcommand has the description optionally set a title for what you're about to write about. Note that --help and -h in structopt mean different things, and that -h will give us shorter, more compact output, while --h will give us longer output. Cargo allows us to execute many different kinds of tests, including integration tests, unit tests, benchmark tests, and documentation tests. For now, we're just going to talk about integration tests for our CLI. Integration tests live in /tests in your project directory and only have access to the public interface of a crate. To spawn new commands and interact with them, such as the garden binary defined in our cargo toml, we'll use assert command. We'll add it to our dev dependencies because we don't intend to ship this with our project. Now, even though we have no tests currently, we can still run cargo test. Note that we've run 0 tests, and the test result is okay. We'll create a new file at testintegration.rs. This is where integration tests live. And although the file name does not matter, the directory name does. To spawn the garden subcommand, we'll use command from the assert command crate. Tests are just like regular functions, except they have this attribute macro on top, letting cargo know that they're a test. This allows us later to abstract functionality into other functions that don't count as tests. In this case, we'll use a utility from the assert command crate to pull out the garden binary from the cargo toml and build it. Now we can unwrap this, but we can also return a result here. Note that after bringing result into scope from color air, we can use that result as the return type. We can then continue to use the question mark instead of the unwrap, but at the end of our test, we'll have to return one of the result variants, in this case, OK, with the value unit, which is what's specified in our type signature. Since we have a mutable command here, we can continue to add arguments, like help, and then we can call assert on that command to give us an assert value that then we can use to test against the successful execution of the binary itself, and do things like check to make sure that standard error is equal to an empty string. If we cargo test now, everything works. There's another trick we can use. If we cargo install cargo watch. Now I already have it installed, so you'll see a couple of dependencies installing here. If we cargo watch -x test, cargo will run our tests and then wait for anything to change. If we add another test, in much the same way that we did the first one, but this time call out to the right subcommand and pass help to the right subcommand, we can see that 2 tests have passed. Finally, if we want to test the right subcommand itself, we can take --help off and actually execute the right subcommand. Note that this panics because we haven't finished the functionality of the right subcommand, and that it's still panicking on not yet implemented. Also note that we don't have to return a result here. If we ignore this test, we can see that test right is ignored, and we have 2 passing tests. We've also seen that we can choose to unwrap, which will panic, or return the error, depending on if we want a result type returned or a unit type returned from our function. From here, I'm going to use cargo watch, which we installed in the last lesson, to run check and then test. To continue the implementation of our CLI, we can match on opt.command. That is the structopt command field. Match lets us match the structure of the value that we're matching on. In this case, we can match on the structure of command write, such that whenever the write variant of the command enum is used, we execute some code. In this case, it will be to do. And I'll remove the final to do. Note that we're also destructuring title here. But cargo check gives us an error. We get the error use of moved value used here after move, title. And the move occurs because opt has typed opt, that is the variable name opt has the type struct of opt, which does not implement the copy trait. Since we're not really using title yet, we can use the placeholder in our pattern to say, hey, we're not using this yet, just don't warn us about it. And now we get a slightly better error. The use of moved value opt.command, same move copy, the value is moved here in debug opt, and the value is used here after move in opt.command. This is because we've passed opt into debug, and debug has taken ownership of this value. Because debug has taken ownership of this value and used it, we can't use it after that. We can fix this by giving debug a shared reference to opt. A shared reference means that we can access this value later when we want to match on it. What was happening originally when we didn't have the shared reference is called move semantics. That is, if we use the variable and we give ownership to the debug function, or the debug macro in this case, the variable moves ownership into that function. And we don't get it back after it's done. Passing a shared reference in lets us use copy semantics, which means that the ownership won't get moved into this function and that we can still access the variable later. In our subcommand match, we'll add a new function called write to handle our write subcommand. We'll pass it the argument title, and we'll import it from a library called Digital Garden. Remember to remove the placeholder that we added last lesson. Digital Garden doesn't exist, so we get a use of undeclared crate or module Digital Garden. To create this library, add a new section in cargo.toml called lib. The name of the lib will be digital_garden, and the path will be at source lib.rs. Note the difference between the bin declaration and the lib declaration. Bin is an array, whereas lib is not. That's because we can only have one library crate in our package, while we can have as many binaries as we want. In source, we'll create lib.rs with the following contents: mod write, pub use, write. Now, because I know what we're going to do later, and we're going to add more subcommands in different files, we're going to use a little bit more of the Rust module system than we would otherwise have to. We could export a public write function from this file, and it would work. But instead, we're going to extend this into another file called write. Rust's module system is explicit. So when we write mod write, we're saying that the library Digital Garden, which comes from the librs file, has a module called write, such that the path to the module is Digital Garden : write. In our case, Digital Garden : write corresponds to a file at source write.rs. So we'll create that file now. Back in lib.rs, pub use write says that we have a function called write in the module called write that we just defined, and that the function will be exposed publicly. So people who have the Digital Garden library installed will be able to use the write function from the write module as Digital Garden : write. If you're used to JavaScript, the closest analog is export write from write.js. By using use, we're effectively shortening the import path to the write function. In write.rs, we'll create a function called write with a visibility of public that accepts the title that is an option of a string, which is the same argument we passed in earlier, and returns a result just like all of the other results in our application. Inside of this function, we'll leave our to-do, as we're not done writing this function yet. And we can see that our tests are passing, which means that our write function is being correctly targeted from our binary crate. To drive the point home a little further, there is a path at digital garden write. That would be lib.rs write. But because the module path in Rust is explicit, and this module is private, while the function is public inside of the current module, we can't reach into write to arbitrarily use functions. We can only use the function that we've publicized at the digital garden level. Okay, so now we have a write function, which is what we're going to use to write files out to disk. But we don't know where to put them yet. So we'll start by going back to main.rs and writing a little utility function. The function name is going to be getDefaultGardenDir, and it's going to return us a result with a pathbuf. This means if everything succeeds, we get a path buffer, and if it fails, we get an error. We're going to take advantage of the directories crate to get the user directories. If we can find a home directory, we'll join it with .garden to give us the location of the user's default garden. This will be home directory /.garden. Since I'm using Rust Analyzer, I can use command dot on a Mac to bring up this little menu and import standard path pathbuf. If I scroll up, you can see that it used standard path pathbuf for me. We can't do the same for userdirs because the crate isn't installed yet. So let's stop our watch process and run cargo add directories. And then we can start our watch process again. Note that cargo check was telling us that we might want to use directories userdirs because we are using it in our function. We have one more identifier to bring into scope, and that's air. We can use the Rust Analyzer autocomplete to import from color air, but that's not actually what we want. So we have to go up and fix it. What we want is color air, which is a macro. It's a macro for creating new errors. Userdirs new returns an option. So we can turn that into a result with OK or else. OK or else takes a closure that takes no arguments and allows us to give an error value. This is important because we're adding context to why the userdirs failed. Note that because we have a result after using OK or else, we can use the question mark to early return if there's an error. If we have a valid userdirs value, we can get the home dir and then join it with the garden. Ideally, we don't just supply the location of a garden. The user will probably want to specify that themselves. Using structopt, we can let them specify it as a short or long flag or an environment variable. If we go back to our README, we can specify how this should work. Under commands, we'll add a section called setting the garden path. And this will allow us to specify the environment variable as a location to garden right, specify a short flag, -p, or a long flag, -- garden path. Back in our opt struct, we can tell structopt exactly what we want to see. Garden path is going to be an optional pathbuf because the user can supply it or not. The short version is going to be p, the long version is going to be automatically derived, and we're also going to be able to specify it as an environment variable. Note also that we've used a custom parse function because path buffers are OS strings. OS strings can include characters that aren't valid UTF-8. Back in main, we can specify the garden path as the result of a match on options garden path. Options garden path being an optional type. If we have a path buffer, we're just going to return that path buffer, and that will become our garden path. This means the user specified one. If we match and there's none, then we're going to get the default garden dir. This is a result, so we'll wrap this in an additional error context. Wrap error takes the error that happened and places it at the source of our new error, adding additional context to what went wrong. To use wrap error on a result type, we need to bring in the wrap error trait from err. In Rust, functions that are added via traits aren't accessible unless the trait is in scope. With our tests passing, we'll choose to force an error and get default garden dir to see what this looks like. Here we can see what happens if an error occurs in get default garden dir. We can see garden path was not supplied, which is the context we wrapped our error in, and we can see the original error. While we forced an error here, the error that would normally occur is this could not find home directory, which is the message that would appear in error number 1. So the user will get the information that the garden path was not supplied, and we also couldn't find the home directory. If both of those occur, then we don't have a place to put the garden, and the CLI tool cannot continue. We also have to change the signature of our write function to accept the garden path. We'll add the argument here, which Rust Analyzer is correctly telling us doesn't accept 2 arguments right now. And we'll change write to accept pathbuf as the first argument. Again, we can use the Rust Analyzer command dot to do the import for us, or we can write it out ourselves. I'm also going to debug the garden path and the title, so we can remove this placeholder. With everything type checking and our tests passing, we'll run write. And now we can see the opt struct and which subcommand we used logged out, as well as inside of source write, the garden path, which for me is userschris.garden, and the title that was given. We now have a user configurable garden path. If I wanted the garden path to be somewhere else, I could just say so. And note that the garden path will come in as somewhere else. So what user experience do we want for the act of writing? At some point, we have to pass control to the user, and they have to do something to put some writing down on the page. We have a few options, including letting users directly write into the console, or giving them a prepared file that they can open and write in. Writing directly into the console doesn't give a user access to their text editor of choice, which means lacking autocomplete, syntax highlighting, snippets, and other functionality they might be used to. Creating a file and handing the path back to the user doesn't quite work for us either, as that reduces the utility of the garden write command to the equivalent of running touch filename.md. So for our use case, we'd ideally like to open the user's preferred editing environment, whatever that happens to be, then wait for them to be done before continuing. Since we're working with a CLI tool, we can safely assume that our users either know how to or are willing to learn how to set environment variables. This means we can use the editor variable to select an editor to use. This is the same way that git commit works. Note that I have my editor set to Emacs client right now. I won't be using Emacs client today. I'll be using vscode, and I'll show you how to set the editor variable in line with the command in case you don't have one set either. In Rust, there's a crate that handles not only editor, but also various fallbacks per platform. We'll take advantage of edit to call out to the user's choice of editor. The quick usage of edit, shown in the documentation, allows us to call the edit function with a template, and then it gives us back the data the user wrote, which we're debugging here. Note that the wrap error trait is not in scope, which is why we're getting an error here. If we set our editor variable inline to code and run cargo run write, we can see that our program actually exits early, while the file is still open. That's because for vscode, we have to use code-w, and then we can write some code here. Take note of the file name, which is .tmp with a hash on the end. And it's actually in a completely different location. In this case, it's in var folders hw, a bunch of gobbledygook, and then .tmp. If we save this, close the file, it'll return control to our program, which we can see was successful. Content from user is exactly what we wrote. But we have no idea where this file really is as a user. The only reason we know is because vscode happened to tell us while it was open. That temp file is in a location no user would reasonably find it. Ideally, if anything went wrong, the user would be able to take a look at the in-progress temp file they were just working on, which should be in an easily discoverable place, like the garden path. Above all else, we don't want to lose a user's work. Additionally, the temp file doesn't have a file extension, which means that while I was writing Markdown, the user's editor, or my editor is vscode, is less likely to recognize it as a Markdown file. So we want to add .md to the file path, because that's typically how editors determine what language highlighting to use and which mode to be in. What we're going to do is drop down to a lower level in the Edit API, using Edit File and Builder. Builder allows us to build a temporary file with the suffix of our choice, .md, some random bytes, like the random bytes we saw in the file name earlier, a location for the temp file, which is going to be in the garden path now. And instead of making it just a temporary file that closes out when this function goes away and gets deleted, we can keep it and make it persistent if anything goes wrong. This Builder API returns us a mutable file and a file path. To get back the idea of inserting a template into the file for the user to then fill out, we can use write all on file. Note that write all is part of the write trait, so we need to bring that into scope from standard IO write. We've also made the template a const because it never changes. Consts are usually specified in all uppercase, and the type of this const is going to be a slice of U8s of length 2. If you don't know what a slice is, it's not super important right now. Just keep in mind that this is basically an array of length 2. We can use the B on the front of the string here to make it a byte array. Also note that we have 2 characters in here, which accounts for the length of 2. Also note that we have a couple results that come in while we're using this Builder API, and we've wrapped them in more context at each point that they could fail with wrap error. Error allows us to keep chaining as long as we have succeeded in the previous call. If we fail here, we'll return with an error from this function. If we fail here, we'll return with a different error. If we change the string here, say add another couple characters, we can see that the length of the byte array is checked at compile time. So instead of 2 elements, right now we have 8. We could change the type to be a length 8. If it's length 8, it'll pass and compile. But we don't need these extra characters, so we're going to get rid of them and return to length 2. And now we can use the edit file like before, passing in the file path that we just constructed using the builder. This is now a much more specific file path that is in a much more discoverable place for the user. If this fails, again, we return the error using the question mark. Now, since we already have access to the file, we're going to read that to string, but we need a string to put it into. So we create a mutable contents that is a new string. If we pass a reference to the mutable contents to the read to string function on file, what we end up with is contents filled with the file contents, which we can debug out. And note that we get some nice syntax highlighting, as well as some heading highlighting because of the file extension. I even just got auto format on save, which inserted that semicolon for me. Now we can see the file contents being logged out on line 27. And now we've let the user write using whatever editor they want and all of the comforts of that editor. And we've also kept the temp file around, meaning that if anything goes wrong, as it just did because we panic, the temporary file lives in our garden, where we can easily find it if we need to. This means if the user sees that something happened with the application that we've written, they can go into their garden and look for this temp file and see if there's any of them laying around the disk. Then they can recover them and choose to rename them and keep them if they wish. After getting the user's input, we need to figure out a file name to write the file out as. We can either use the title the user passed in, or we can try to use some heuristics to find a title from the markdown content they just wrote. We can combine the user's title from the CLI arguments, which they may or may not have passed in and is thus an option type, with the logic we use as a heuristic for the markdown, which will also be an option because we may or may not be able to get an answer out of it. Title is the first optional type. It's the one the user passed in or didn't pass in to the CLI. The or else function on options will return the original option if it's a sum value, or execute the closure to return a different option if it's none. So document title is an option string, as Rust Analyzer is telling us here. And either way, we've covered all of the possible scenarios. If the user passes in a title, we get title. If the user has written content with a heading, we use the internals of this closure to find that heading and return it. And if the user does neither of these, document title will be none. Which leaves us to talk about our markdown heuristic. We can take the contents of the file that we just read to a string and turn it into an iterator over lines. Now, so you don't have to read the markdown spec, I'll just tell you that in the markdown spec, ATX headings have to start with a hashtag or an octothorpe, followed by at least one space. This is not true for all possible headings that you can put into a markdown file, but it's true for the primary heading if it's an ATX format. That's what makes this a heuristic. Contents.lines gives us an iterator, which we're using .find on, which gives us a line. On each line, we test to see if it starts with the hash and a space. If it does, then we use .map to map over that. Find returns us an option. So map will let us operate on the value inside of the sum if there is one. If it's none, this map will never execute. Given a line, we'll want to trim off the starting hash and then the space. And we want to match the type of the title, which is a capital S string. So we'll use toString because we can see that trim start matches gives us a string slice. And we need to convert that into an owned string or a capital S string. So let's give it a go. We can see our options got debugged out. We can start writing a heading, some content, save, exit the file. Our program crashes as expected because we still have to do at the end. We can see that the file contents are here and the document title is none, but it shouldn't be none. It should be a heading. If we look at the contents of the file here, we can notice a bug. When we wrote to the file with write all using our template, it seeked the internal cursor of the file forward 2 bytes, which means that when we read to string, we're reading from a 2-byte offset into the file because we haven't reset that seek. And thus, we don't get the initial hash for our heading. To fix this, we can seek on the file right before we try to read the whole thing. Note that this will require bringing seek from into scope, which will seek us from the start of 0. And we also need to bring in the seek trait, which is what will allow us to use this seek function on the file. Without bringing in seek, we won't get the seek function. And without bringing in seek from, we can't construct this start value. And now we can see that we've seeked to the beginning of the file, we've debugged out the entire contents of the file, and our document title gives us sum a heading. Given the potential document title, we now want to ask the user if the title is still what they want to use so that we can write the file to disk. This will involve 2 paths, depending on if we have an existing potential option in document title or not. We'll match on document title, and if we have an option, we're going to ask the user to confirm the file name. For now, we'll leave that as to do, and we'll move on to ask for file name, which is the case where we don't have a document title, which means the user hasn't passed one in, and they didn't type enough in the markdown file to actually let us use our heuristic to find a title. We're going to start with ask for file name as opposed to confirm file name, because ask for file name will be used inside of the confirm file name function. We're going to add another package called rprompt. Note that our ask for file name takes no arguments, but returns a result of string. We'll use rprompt, and specifically prompt reply standard error, to ask for a file name from the user. Note that this is a 2-line query. First line will have enter file name, and the second line will just have an arrow. I've used a backslash to give us a new line, so that both of these are on the same horizontal column in our source code. Note that rprompt returns a result, so we don't need to do much here, but we do want to add a little bit of context, just in case something goes wrong. This again uses the wrap error trait from color error, and we say, failed to get file name. Next, we'll implement confirm file name. Again, we create a new function. This time we want to pass in the raw title, which will be a string slice. If we go back up to confirm file name, we can see that we have a raw title inside of this sum, which we've destructured out of it. We'll add it as an argument here. Cargo check does tell us there's a problem with this, because we've defined our confirm file name function to take a string slice, but we've passed in a string. We can see it's a string because Rust Analyzer tells us here. Cargo check tells us to consider borrowing here, which is what we'll do. We can turn a string, capital S string, into a string slice by borrowing. Inside of confirm file name, we'll use a control flow construct called loop. Loop will infinitely loop until we break. When we break, we're allowed to give it a value to break with, which will end up, in this case, because loop is the only expression here and we haven't included a semicolon, the break value will be result of string. Again, we'll use a similar pattern with rprompt, prompt reply standard error. In this case, we'll use the format macro to ask the user if the current title, which we pass in using the display formatter, is good enough for them by asking, do you want a different title, yes or no? We've capitalized N because N is the default value if they just hit enter. This is a convention and it really isn't enforced anywhere, but it's good enough for us for now. Remember that our prompt reply standard error returns us a result, so we can wrap that result in an error to give it more context. In this case, we'll let the user know that we failed to get input for a yes or no question. Given the result, we'll match on the result as str. I use as str here because string literals are string slices in Rust. And this saves us a little bit of typing because we don't have to do string.from to get a capital S string or an owned string. Inside of a match, we can use multiple patterns. So in this case, we're checking to see if it's Y or capital Y. If it is, then we'll ask for the file name and break with the result. If it's N, lowercase, N capital, or the user hasn't given us any input, we'll break with an OK of a slugified title value. And if neither of those occur, we'll loop through again and ask again. The break syntax might be a little bit confusing if you haven't seen it before. Remember that in Rust, most things are expressions, and expressions return values. So in this case, what we're doing is saying we're going to break out of this loop and return the value that is returned from this function call. So the return value of loop becomes the return value of this function, which, because it's the only expression in confirm file name, also becomes the return value of the entire function. A similar thing is happening down on line 79, where we break with an OK value. OK is a result variant. Now I also have slugify in here, which is a package we haven't added yet. The reason we have this is because while file names can technically have spaces in them, we're going to slugify our file names like URLs for a few reasons. One is that when starting out, many programmers fail to quote file name arguments in their bash scripts, which results in file names with spaces being treated as separate arguments, which can be confusing and hard to diagnose. Since this is a CLI tool, we want to make sure that this is as palatable as possible, especially to new programmers. Another reason is that this is a digital garden CLI, and digital gardens are often stored in Git, accessed from multiple different file systems, as well as from URLs. While strictly speaking, we don't need to slugify our file names, especially since most modern systems can handle spaces correctly, we will here so as to adhere to a safer set of characters. We have to add the slug package. In confirm file name, we've already used it, but in ask for file name, we still have to. Remember map that we used before can be used to map over the value inside of a structure. In this case, we're mapping over a result. If it's OK, then we take the value inside of the OK variant and we slugify it, returning the OK variant with the new value inside of it. If it's an error, map won't touch it, because map only operates on OK or some values. That is, values inside of structures that represent success. The fact that ask for file name and confirm file name are both result strings with a capital S is no accident. The match on the document title, the return values for confirm file name and ask for file name in each branch of the match must have the same type to be valid. If they had different types, this match would fail to compile. We'll add in a debug of contents and file name, just to make sure everything works. And we can see that if we have a title, we get current title heading here. Do you want a different title? If we say no, the program will end. So we'll say yes, which kicks us into the ask for file name cycle. The program gives us enter file name and the opportunity to enter one. The contents of the file include the heading, which is what we pulled out before for the original title. The user, however, told us that they wanted a different name, which is my awesome file, which we can see here. And this is how we can interact with the user for quick back and forth. The next thing we want to do is take the file name, which we can see Rust Analyzer is treating as a result string report, which isn't actually what we want. If there's an error here, we want that error to propagate back through the function. So we'll use a question mark to do that. Then we're going to write a loop. We used a loop already, so I won't explain too much about that. But we're using this loop to format a new file name that is unique. We need to do this because if there's a file with the same name as the user wants, we don't want to overwrite that file. The approach we're going to take is if we have a file named hello.md that already exists and the user wants to write out hello.md again, we're going to give them hello1.md, which preserves both files. We can start out with the number 0. This is going to be a mutable variable because it will increment until we hit a number that gives us a unique file name. We'll use format again with 2 display formatters. One will be the file name that we got from the user, and the other one will be a number. In the case of 0, we won't add anything to the file name, so we'll make this an empty string. In the case of it being greater than 0, we want to add the number, so we'll stringify the number and put it into the format. This gives us a destination file name of hello1. We're going to finish off the rest of the file name by joining the garden path to the destination file name. This gives us a mutable path buffer on which we can set the extension of this file. At this point in the code, what we have is a path to the garden path and a file of hello1.md. Path buffers include a function called exists that allows us to detect if this file already exists. So if we have hello.md here, dest.exists will return true, and we'll increment I and loop back through again, trying with hello1. If it doesn't exist, that means we can take the temp file that we had before and rename it into the official location in the garden path. Note that we have to import fs, which is from stdfs. Rust Analyzer helps us out a little bit, but we get a used here after move when we try to use the file path on line 65. This is because all the way back up here, when we got the file path from the builder, we passed it to edit file. Now these are the same semantics that we came across earlier in this course, which are called move semantics. Move semantics are the default in Rust. In this case, we're moving file path into this edit file function. To use copy semantics instead, we can pass a reference into edit file. And if we save, we can see that later on, we can use the file path in our rename function. So our code checks and the test pass. So let's give it a whirl. Also note that we're returning OK with unit if everything that we've written succeeds. We'll run our write command with vscode. We'll give it some title and some content. We'll save and exit the file, which returns control to our program. The current title is some title, and I think that's going to be okay for me this time, so I'll just hit enter. So now if we look in our garden, we should see a file with some title with the content, a heading of some title, and on line 3, some content. This is in fact what we see, so our program has succeeded. Let's review what we've done so far. In main.rs, we've installed colorize to give better error messages. We get the options using structopt from args, and then we debug that out. We no longer need this debug, so we'll remove it. If the user passes in a garden path, we'll use that, and if not, we'll get a default garden path. If anything fails, we'll wrap the error with additional context for the user. Finally, we'll match on opt command and use destructuring to pass the garden path and the title into our write function. Our write function lives in a file called write.rs, which we're re-exporting from lib.rs. We use a builder to build up the file with the appropriate extension and a couple of other configurations. We write out a constant to the file as a template, so when the user opens a file, they have something to work with. We pass the control to the user using the file path we just created. And when they're done editing the file in their editor of choice, we make sure to seek back to the beginning of the file and read it into a string. Given the fact that a user can choose to pass in a title or not, we combine multiple options together and try to find a title that we can use. If we do find one using either our heuristic or from the user, we ask the user to confirm at this point because they've been writing for a while and maybe they changed their mind about what they're writing about. If we can't find one and they didn't pass one in, we ask them for one. And finally, once we have a file name and the contents of the file, we find a unique file name that we can write out to disk without conflicting with other files. Finally, renaming our temporary file in the garden path to an actual file in the garden path. We have two functions for interacting with the user and printing lines to the terminal to ask them for input. Let's make this a little bit nicer to use by adding colors so that the user can differentiate between different pieces of the input. We can do this by bringing an extension trait for formatting into scope called colorize. In this case, colorize re-exports it so we can pull it in from there. But it's also its own package if you want to use this in other projects. Extension traits are one-off traits that are used to add functions to a type that our crate doesn't own. A crate can create the new trait, then implement the functions defined by that trait on a type the crate doesn't own, and if we bring that trait into scope like we just did, the type will get the extra functions. In this case, colorize is used for adding color functions to formatters like display and debug. We'll start with ask for file name. To access the extension trait functions, we need to use a format. Now that we've introduced the format macro, we'll add a display formatter. This means that the string that we're passing in here will be formatted with the display trait in this string here. This allows us to use the extension traits on this string, which we can then do to make it blue and bold. In confirm file name, we'll do a very similar thing. making 2 display formatters, and some additional text where we're asking for user input. We'll pull out current title and make it green and bold. With cargo checking and all of our tests passing, we'll now take it for a spin. We can see that current title is now green and it says some heading. Do we want a different title? Well, yes, we do, because we want to see the other input, which we can see is now blue and also bold. This gives user input a different color than the program output, helping to differentiate the user's own input from what the program is asking them to do. If we go back to our integration tests, we'll remember that 2 of them are passing and we ignored one early on that was meant to test whether the write command actually worked. We're going to write this test now, so we can get rid of ignore, and we'll see it fail on the right. In this case, the failure mode is that it just waits for user input forever, which is really unfortunate. We'll kill the watch process so that doesn't happen anymore. And we'll test manually for the moment. The first thing we want to do is create a fake editor script. We'll call it fakeeditor.sh. And what this is the program that we're going to execute as the editor. In our command line usage, whenever we test it manually, we've been using editor equals code-w. This program is going to be that editor. In this case, all it's going to do is echo testing to whatever file name it gets. These 2 arrows mean that it will concatenate to whatever's already in the file, which means that our template is preserved as well. Then we'll write our test using the assert command to build up a command that points to the garden binary in our cargo toml. We'll get rid of assert for the moment and add in a way to get the fake editor path script. In this case, we can use the current dir. We'll expect that we can get the current dir because this returns a result. If we can't, this test will fail. We'll join tests because current dir is actually the root of our package. And we'll join with fakeeditor.sh. This gives us a path buffer, which we can use to check to see if the file exists. This gives us an early indication about whether we got the path for the fake editor script correct or not. If it's not correct, we'll panic and say, hey, we couldn't find this fake editor script. Additionally, we'll take the mutable command that we have, which is calling our garden bin, and we'll add the editor environment variable with the fake editor path. We turn the fake editor path into an OS string and place it into the environment. Then we add an argument of write, a -t for the title flag, and an argument a title. This is the same as writing -t a title on our command line. Because we'll already have a title, the only thing that we'll need to do here is write to standard in with an N and an enter key, which is a new line here. Write standard in takes bytes, so we'll turn our string slice into bytes, and that will respond to rprompt for us when it asks us for input, saying, no, this title is okay. We use .assert to give us the assert so that we can say, hey, this binary exited successfully. And now if we cargo test, we'll actually see something kind of unfortunate. This is not a good error message for what's actually going on. Because I know the internals of the libraries that we've used, I know that Nano is one of the default platform choices for Mac OS for the edit package that we used earlier. That means it's failing to use our fake editor script. In this case, it's because our fake editor shell script doesn't have executable permissions, which we can give it with chmod +x and then a path to the fake editor script. Now when we test, we can see that the test actually passes. We do have a problem here though, in that if we look in our garden for atitle.md, for some reason it's there, And no matter how many times we run this test, we'll keep getting more and more A titles with increasing numbers. You can see that this first A title doesn't have any content, which is the one that didn't work, whereas A title 5 is a successful test. So there's a couple of problems here. One is that we're making our default garden directory pretty dirty just by running a couple tests. And we don't really want to do that because we don't want to mess with it. We want to be able to run our tests on the same system that we're actually using this CLI on. And the other problem here is that we're not actually testing for the file existence. So we don't actually know if this file successfully got written out. All we know from this test is that the command did an error when it ran. We can solve this with assertfs and predicates. Assertfs will let us create fake files and fake directories that we can run our tests in while interacting with a real file system. And predicates will help us to test if the files that we expect to exist actually do exist or not. To change our test to use a temporary directory somewhere on our file system, we need to use assertfs tempdir new, which will give us the temp directory. And then we also need to add the environment variable for the garden path to point to that temp directory, which we can do with tempdirectory.path. Finally, we want to use tempdir.child with the file name that we were looking for to look for this file name inside of the temporary directory. We don't know where this temporary directory is, so we have to access this using .child off the tempdir. And we can also assert that the path exists using the predicate from the predicates crate. Note that for these to both work, we have to bring in the preludes. A prelude is an import from a library that the library author thinks is going to be useful to just have in scope all the time. So both of these preludes include a bunch of functions and other traits and things like that that the library authors think you'll want when you write tests with these libraries. The star means that we're importing the entire prelude, which is all of the exports. And now when we run cargo test, we'll download the packages and we can see that our tests pass. If we look in .garden now, before we run the tests, we can see there's no A title files. If we look after we run the tests, we can see that there's also no A title files, which means that we're successfully using the temporary directory to write our files into. While we have test write, which tests our application's write subcommand with a given title flag, we can also set up additional tests, such as for using a written title in the document for the file name instead of passing one on the command line. I'm going to copy and paste this entire test and name one test write with title and name the other test write with written title. Both of these tests currently pass because they're exactly the same code. So let's start by fixing the second test and removing the title flag. This will cause our application to write out a file called testing.md, which is the content of the heading in the file. As a reminder, our fake editor echoes testing to the end of the file, which will result in #space testing. And we can see that our test is panicking and that we've failed the exists test on the file. In this case, we can rename it to testing.md, and all 4 of our tests are passing again. This still leaves us with a lot of duplication between these 2 tests, and that's a lot of room for user error. It's also a lot of room for refactoring pain if later we want to change anything about how these flags are handled or how this fake editor path is going to be inserted. So let's abstract the creation of the temporary directory on line 27, the fake editor script path on line 30, and the command itself on 29 into a utility function. We'll have a function called setupCommand that will return a command in a tempdir. The port is relatively straightforward, and by that what I mean is that we haven't made structural changes to the functionality of any of this code. We still create the tempdir, we still create the command, we're getting the fake editor path in the same way, we're checking if it exists, and the only real change here is that we've cut off the environment variable definitions from being in our test to being in our helper. That means our editor and garden path will get inserted by this helper instead of by our test itself. To return multiple values from a REST function, we have to return a tuple. We could also set up a struct, But this return value doesn't really deserve a name. We're only using it as a helper. So we're going to use a tuple, which allows us to put two different type values in the first and second slots. And now if we use our setup command instead of a bunch of the code that we had there before, and we also have removed the environment variable declarations from our assert, we can still chain our arguments on, chain our standard in, and assert on the output. We'll do the same for the other test. Again, removing the environment variable declarations. And that's it. Now we have a helper that we can use to create any number of tests beyond this. As a final note, I'll say that this setup command isn't run as a test itself because it doesn't have the test attribute like we have on line 25 here. Line 5 that has no attribute. So this is not recognized as a test.